Hello. Today we're going to look at mid-segments and coordinate proofs. And coordinate proof, don't get worried, it's not a whole new kind of proof. It's pretty much what you're already used to. Just a big name. Won't be that tough. But of course, this is mathematics. If we have mid-segments, we must have a theorem about mid-segments. What's the point of having a mid-segment if you can't make a theorem about it? What is a mid-segment? Well, you take a triangle. We got lots of those, right? You find the midpoint of one side. You find the midpoint of another side, and you connect them. And that's a mid-segment. And there are a couple of interesting things about mid-segment. Number one, it turns out to be parallel. To the, I guess you call it the opposite side. The side that's not connected by the mid-segment. You get two sides that are connected, one that's not. It's parallel to the one that it's not connected to. You can look at it that way. And it's exactly half as long. Cool, huh? Well, at least maybe interesting. It's less obvious than some of the other things we've done in this class. So let's check this out. See why this would make sense. And at the same time, we'll figure out what a coordinate proof is. Coordinate proof is really pretty simple. All it means is you lay it out. You lay out your objects on a coordinate plane, give them coordinates, but general, in other words, variable coordinates. Use the variables to demonstrate your conclusion. If you can do it with variable coordinates, then it will work with any coordinate. Much the same way we do algebraic demonstrations or proofs. For instance, if I say that, put it over here, two plus 3 quantity squared is 2 squared plus 2 times 3 plus 3 squared. Now I can work that out. And it'll, I believe, turn out to be true. Certainly hope so. Let's see, this would be 5. This would be 25, right? What's this going to be? 4. And 6 times 2 is 12. And this is 9. And 9 and 4 is 13. And 12 is 25. So it's true. Well, that's not much of a proof, is it? I mean, I just put two numbers in here. As long as the first number is 2 and the second number is 3, this expansion is definitely true. But suppose I put a 5 and a 6 in here. What then? Wait a minute. I got an idea. Suppose we did it like this. Now, I can write out an expansion that you're probably familiar with. And the important thing about this expansion is it didn't matter what. X is any real number. Y is any real number. So when I write this expansion, it must be true for any real number. And that's basically what we're going to do with a coordinate proof. We just pick variables which correspond to any real number. We don't know what they are. If our conclusion turns out to be true for variable coordinates, that's the same as saying it's true for any real number. Or, in other words, it's true. So you see, coordinate proof has a big name, and it sounds like a big deal. It's not that big a deal. You're already familiar with what you would do with a coordinate proof. So let's do it. Remember how we found midsegments way back in chapter 1? You probably don't. So we'll do it again. If we have a line, and let's say we have endpoints. Well, that's not a very good line because it's horizontal. Remember, if we had a line here, we had coordinates AB for one endpoint and CD for another. We found the midpoint by taking basically the average of the two coordinates. For instance, the x-coordinate of the midpoint was A plus C divided by 2, and the y-coordinate was B plus D divided by 2. So we found the midpoint of our x-coordinate, be right there, and then we find the midpoint of our y-coordinates here. We could say we find the midpoint in the horizontal direction, and then find the midpoint in the vertical direction, and where they meet will be right here at the midpoint of the line segment, which has those coordinates as endpoints. Well, we're going to apply that here. Now, finding the mid-segment of this section should be pretty easy because we got a 0, 0 down here. So, what's this midpoint? Well, I'd say it was B plus 0, or B over 2, and C over 2. And that's right here. It's our midpoint. What about over here? Well, over here we get B plus A over 2. And C over 2. Well, maybe I should draw them about the same. There we go. That's our midsegment. Since we're using variable coordinates, it doesn't even matter if I draw it badly. It doesn't really look like it's in the middle. That's okay. We just have to see how our variables work out. Number one, how do we know this is half the length of this? We could start with that. Might not be too hard to show. Let's check it out. This is a horizontal line. They have the same y coordinates. So, all we have to do is compute the horizontal distance here from B plus A over 2 to B over 2. That'll be easy. All we have to do, we don't even need our distance formula, just subtract this coordinate from this coordinate. We get B plus A over 2 minus B over 2. And of course, we have common denominators, makes it real easy. We just end up with A over 2. But this had length A, that's pretty obvious. Goes from 0 to A. So A over 2 is exactly half of that, which is what we were trying to figure out. So it turns out this is exactly half of this line here. Is it parallel? Well, why don't we just check the slopes? Let's see here, rise over run. The rise is 0, so it's not going to matter. We got 0 minus 0, right? Doesn't matter what goes in the denominator, that's 0. What about up here? Well, we got C over 2 minus C over 2. Well, that's going to be 0. These both have a slope of 0. Then they're parallel. It's the nice thing about a coordinate proof. You can use algebra to make a geometric proof. That's basically what we're doing here. They call it a coordinate proof, but we insert variables for coordinates and then reduce our proof really to algebraic expressions. expert on the Midsegment Theorem, and this is what a coordinate proof is. It's really pretty simple. So now let's take a look at some problems. Oh, there's one right now. One of those error analysis problems. Well, some dopey guy who makes geometry videos made a real stupid mistake. What did he do here? He decided that since DE is half of BC, they must be parallel. Wow, he concluded all kinds of things, didn't he? He has a line cutting across the triangle, and it's half the length of this line. From that, he concluded that somehow any line that is half the length of this is a midsegment. Well, no. Midsegment has to connect the two midpoints. It turns out to be exactly half as long as the side that it's parallel to. That doesn't mean that every segment you draw, which connects two sides of a triangle and is half the length of the third side, is going to be a midsegment. That's completely wrong. You can't go both ways. The midsegment is half the size of the one it's parallel to, or you could say the third side. However, the segment connector, which is half the length of the third side, is not necessarily a midsegment just because it's half this length. You can't go both ways with it, and I think that's what he's trying to do here. Bad dog, no biscuit. Okay, I went ahead and plotted the points. We've got midpoints of a triangle are at 2, 0, 7, 12, and 16, 0. Our job is to find the perimeter of PQR, which is, maybe I should have labeled that PQ and R here, which would of course involve finding each of these. Well, this one's easy, I think. I'd say this is 14, right? These two, well, looks like we're going to need our distance formula. Shucks. Okay, using our distance formula, we can find the distance from P to Q and R to Q, which would be the length of the sides. So we just plug that in here. We could just take this point as P2 and we get 7 minus 12 squared plus 12 minus 0 squared. And that's PQ. And for the other side, we get 7 minus 16 squared, 12 minus 0 squared. That gives us that. This is 25 plus 144. It's the square root of 169, which is 13. This would be the square root of 81 plus 144. That's 225, and the square root of that is 50. And we can go ahead and put those in over here if I want. So, what is our perimeter? 13 and 14 is 27. I think it'll be 42, right? Let me double check that. 42 is right, and that's the perimeter of PQR. But this triangle was made up of midsegments of some other triangle. what would the perimeter of the other triangle have been? Well, gee whiz. Each midsegment is half of the third side. So there's a side over here from some triangle, and it's parallel to it. That's double the length of this. There's another side over here that's parallel, and half the length that runs along here. And there's another side parallel to this that's twice as long and runs along here. So this imaginary triangle I just drew in the air here would have a perimeter of 2 times this plus 2 times this plus 2 times this. Very simple. So if we double each of these and add them up, we'll get 84, which is exactly double this. And that makes perfect sense. If we put variables in here for our midsegments, say we call them A, B, and C, and then capital A and capital B and capital C for the original triangle, then we have A equals 1/2 of capital A, and on down the line, B is 1/2 of capital B. So, when we add up A plus B plus C, the lengths of our midsegments, that's the same as 1/2 A plus 1/2 B plus 1/2 C. Now our distributive property means we can factor that out, and we get 1/2 of A plus B plus C. So the perimeter of our midsegments is always going to be half of the perimeter of the original triangle. And in this case, we just had to go backwards. We knew the perimeter of the midsegments, the triangle created by connecting all the midsegments, and we just went backwards and doubled it the same way we would here. If we had this, or pardon me, if we had this and wanted this, we would just multiply through by 2, and we get rid of this and put a 2 in front of here, double the perimeter of our midsegment triangle, and get back our original one. Now what we need to do here is find the coordinates of P, and then show that these two triangles are congruent. And we're going to turn geometry into algebra again by using variable coordinates. Well, this point here is on the same vertical line as this point, which means it has the same x coordinate. So we can put a 0 in there. Well, here we have a horizontal line. The y coordinate is k for this point on this horizontal line. It's k for this point, so the y coordinate must be k. That's 0k, not OK. Now that we have this point, how do we show this? Well, we don't have any angles, because we aren't given any, except this here. We do have a right angle, don't we? And that's okay. Even though they didn't write it in, we can say that it is because of the x and y coordinates. If the x coordinates are the same, that's a vertical line. If the y coordinates are the same, that's a horizontal line. And vertical and horizontal lines are perpendicular. So we can say that this is perpendicular, and maybe even quicken our proof a little bit. Why? Well, now that we know this angle is the same as this angle here, if we could show this leg was congruent to this leg, and this leg was congruent to this leg, we'd be done. That looks kind of easy. This, well, let's see here. Our y coordinate is the same, so k minus k is 0. So the distance from here to here is just h minus 0. So we'll, that's the length of this segment here. What about this segment? Well, the x-coordinates don't change, it's just the 0 to k. So that has length k. What about this here? Once again, no change in the y-coordinates. This is just 2h minus h. Well, sounds like h to me. What about this one? The x-coordinates don't change. It's 2k minus k. Well, son of a gun. We got k here, h, h. And so by, you can pick which theorem you like. Side angle side works. It's more general. Maybe you could pick some specialized theorem about right triangles. I think it's easier to remember generalized theorems. They'll always work for you. You can always go back to them in a pinch. Because anything that's true for a regular triangle is going to be true for a right triangle. It doesn't necessarily go the other way. Right triangle is just a special case of a triangle. But if it's true for triangles in general, then it definitely is true for right triangles. Now this was, I'm sure you didn't have any trouble with this one out. It's pretty easy. They laid it out nice for you so that you could compute these distances without using your complicated distance formula. And once again, we're going to use variables for coordinates. And I didn't even draw in the x and y axes. Why not? Well, we don't know what h and k are. So the axes are kind of irrelevant. Look at it this way. Maybe h is 5,283 and k is 9,659. Well, then our x and y coordinates would be way off the page, wouldn't they? So to keep in mind that everything is totally general here, I'm not going to draw in the x and y coordinates. It has a vertex at minus hk. Let's minus hk. We could pick any one of these to be minus hk, I guess. Let's try this one. Let's say this is minus hk. Now it has a length 3h and k, so I guess we can try labeling it this way, see if that works. Which points cannot be a vertex of the rectangle? Well, let's see here. If this is minus h and k, this would be the point minus h0, wouldn't it? We go, wait a minute, no, pardon me. We go up k, this would be 2k, wouldn't it? I don't see that up here. Shucks. That wasn't a very good choice, putting my minus hk down here. Why? Well, I should have observed that we have k here for our y coordinates and 0 down here. So why not make minus hk our left-hand upper side? Also, we have h here and minus h, so we're not going to go to the left of minus h, and we're not going to go above k. So it would have made more sense to make minus hk the upper left. Or as an author wrote in a math book I read a long time ago, a little bit of thought has been known to produce satisfying results. Yeah, he was a little bit of a sarcastic author, but he had a good point. Well, what do we got now? This point right here, well, the y-coordinate would be 0, wouldn't it? Because this has length k. You drop down k units from k and you're at 0, aren't you? And the x-coordinate would be the same. Well, that's up there. And if I put the given vertex up here, this point is possible. Now this point over here would be minus h plus 3h. Right? It's got a length of 3h, and we're over here at minus h, so we go this way 3 h's, whatever they are, and we'll end up at the point 2h for an x-coordinate, and 0 is still our y-coordinate, and that's up here too. Okay, cool. What would this point be? Well, it would be the same x-coordinate as this one, it's a vertical line. It would be up k, or you could say it would have the same y-coordinate as this one here, which is k. So we have minus hk we already know about. We've got 2h0, we've got 2hk, we've got a minus h0, those are all here. Oh, I don't think we have an hk anywhere, do we? Nope. So, to quote that old author, a little bit of thought did produce much more satisfying results. Just arbitrarily grabbing a point and deciding that's minus hk, that wasn't the smart way to do it. Observing that our bottom y-coordinates are 0, our top y-coordinates are k, our far left x-coordinates are minus h, and our far right is 2h, it made sense to put minus h at the far left and k at the top, which put it up here. Okay, this one, they say show how to find. They don't really tell you to find the vertices. They just say, it's like saying, tell me how you would do it if you were going to do it. Huh. Not actually going to do it. I guess I'd find somebody smart and pay him to figure it out. That's one way. On the other hand, suppose you couldn't find anybody smart. How would you do it? Well, it's not that bad. It looks hard. We have the mid-segments. So, for instance, this is the midpoint of some side. We don't know which side, except that it would have to be parallel to this, wouldn't it? If these 2 points are mid-segments to 2 sides of the triangle, this mid-segment, must be parallel to the other side, and this remaining point must be a midpoint for the other side. So one thing we can do is draw a line that's parallel to this line and passes through this point. Now we have a slope-intercept form. Actually, other forms of the equation, it doesn't matter. The point is, if we know the slope and a point on the line, we have the equation for the line. So we can find an equation for this line and draw it. I just eyeballed a line parallel to this to demonstrate how we're going to do it, because it doesn't say to actually find them, it just says show how you would. Okay, this is how you would do it. You need a line parallel to this passing through this point. Now we're going to do the same thing. You need a line parallel to this passing through this point, and a line parallel to this one passing through this point. And they should all intersect at a triangle which has these 3 sides as their mid-segments, as its mid-segments. let's see what happens. So if we draw these in, we already had this line. Now, we draw a line parallel to this, passing through this point, and then another one parallel to this side, passing through this point. And it looks to me like we have this large outer triangle here, created by the intersection of all these segments. That certainly looks like a midpoint to that, doesn't it? That looks like a midpoint, and that looks like a midpoint. And it should, because we just sort of worked our way backwards. We had all the mid-segments. Now we just drew the lines that were parallel and passing through the third point. And I think that's what they meant, because this says show. And in theory, we have the slope and a point on the line, so we could definitely come up with the equation for this line, and an equation for this line, and an equation for this line. We set the equation for this line equal to the equation for this line, and what do we get? We'll get an intersection point here. And then we set this line equal to this one, we get an intersection point here, and we set the equation for this line equal to the equation for this line, and we'll get this intersection point right here. So you could algebraically do this by finding the equations for the lines, setting them equal, and analytically coming up with the vertices. Make it all algebra and never draw a picture. But that's not what they asked us to do, and pictures are certainly easier than all that messy algebra, aren't they? This is a good problem, because once again it demonstrates the use of indirect measurement. We don't really need the grid lines anymore for this one. Indirect measurement. Triangles are really cool for that. We're going to do a lot more of that in upcoming sections. In fact, we've got a chapter coming up that will involve lots of indirect measurement using triangles. Here's another example of it. We're given that she is standing at the mid-segment. So suppose I draw it more profile. Darn. Okay, here we have this basic triangle just redrawn over here. And we have this person standing right halfway between C and B, and it turns out that her head just bisects this section, AC. Now it says she's standing, and most people stand vertically. And the spotlight hitting the wall, we're going to assume, wow, that it is vertical also. In fact, they give us this little right angle thing here, which says the floor is horizontal and the wall is vertical. And we're going to assume that she's sober and standing straight up, not leaning one way or the other. If she wasn't standing straight up, none of everything we're doing wouldn't work. Why? Well, because if she's standing straight, then she's parallel to the third side here, and her head is bisecting this side of the triangle, and her feet are bisecting this side of the triangle. And her length, well, it says here, I don't know, is it 5 feet? Yeah, there we go, 5 feet. Now, this must be a mid-segment. It's halfway between the two, and it's parallel here, just like a mid-segment has to be. So this is a mid-segment. It's not like that other error analysis problem where the poor guy thought he had a mid-segment, but he didn't really have one. This really is a mid-segment, which means this is half of this, or this is double that. So her shadow is 10 feet tall. Does this mean all shadows are twice as big as the original object? Of course not. It all depends on where you are with respect to the light and where the shadow is being cast. If she moved down here, her shadow might be even bigger. Up here. Well, that's about it for mid-segments and coordinate proofs. The important thing about coordinate proofs to remember is that they aren't that big a deal. It's just like any other proof. It's pretty much like an algebraic demonstration. You use variable coordinates in your algebraic proof, which generally lead to algebraic equations, and the results you're looking for generally fall out as you simplify the equations. So that's all there is to a geometric proof. It's, like I said, it's another one of those big words that doesn't mean a whole lot. Just because the words are big doesn't mean it's really complicated. Probably just means people would like you to think it's complicated. After all, how many people do you know with big names? But they're probably no more complicated than the people you know with short names. Well, that's it for now.